Hello, welcome to Numeristical. My name is Brian Lucena. Today we're going to talk about evaluating classification models and give an overview of that subject. So, how to evaluate a model? When people ask that question, they're usually asking something kind of simple, which is my model good? However, whether or not a model is good could mean different things depending on your perspective. One perspective might be, is my model close to the truth? So the idea here is that there's some objective reality out there about how nature is creating this data, and you want to know, is my estimate of the probabilities of y given x close to the true probability distribution? However, you might be asking a more practical question, which is just, is my model practically useful? And these two questions are not always in alignment. You may have a model that is very close to the truth and captures reality very well, but it's just not powerful enough. The reality is there's just not enough signal about y in x. And therefore, for your particular use case, the model is not practically useful. Similarly, you might have the case where your model is not a very good representation of reality, but it's good enough for your particular use case. It gets the job done. The good news is that typically, when you improve the model by getting close to the truth, you should make it more practically useful. So we're going to start exploring these questions and give a framework for how to evaluate them. So here we're going to start talking about what I call a model performance continuum. So we're basically just going to define an axis for model performance. And we're going to say that better predictive performance lies on the left-hand side of this axis. So at the extreme left-hand point of this axis, we have perfect prediction. What does perfect prediction mean? It means that for every value of x, you're absolutely certain of the value of y. So this is an ideal state. And it may or may not be achievable depending on your particular problem. We talked previously about high signal and low signal problems. And in high signal problems, you might be able to achieve close to perfect prediction. But for low signal problems, you certainly will not be able to achieve perfect prediction. And so typically, the truth lies to the right of perfect prediction. We're not going to be able to achieve perfect prediction. We hope to be able to come close to it, but our bound, the truth, always serves as our lower bound. We can never do better than the truth of the situation. On the other side of the axis, we have what's called the naive model. And the naive model means we're going to guess the same thing for every x, but we're going to have access to the probability distribution on y in order to answer that question. So imagine a situation where you're given a lot of training data on, say, loan defaults, and you find that in this population, 10% of the people defaulted on their loan, and now you're asked to make a prediction on a new person, but you're not told anything about the person. Well, then all you could do is say, I'm going to guess their probability of defaulting on the loan is 10% because you don't know anything else about them. So that would be a naive model. You know the relative distribution of y, but you don't know anything about how x relates to y. Well, what could be worse than that? That sounds pretty bad. What's even worse is what I call the ignorant model, where you're just guessing a single value for every x and every y. You really don't know anything. So you don't know what the problem is. You don't know what 0 represents, what 1 represents. You don't know which is more common. So all you can do is guess 50-50 if it's a binary problem for every single x. So that's kind of the extreme, absurd situation of the worst possible predictive scenario. And somewhere between the naive model and truth is going to be your current model that you've built. Hopefully your model is doing better than the naive model, otherwise you're really in trouble. And your model can never do better than the actual truth of the situation. Let's review some preliminaries and some notation that we have defined previously. We've got our predictors represented by x. We've got the target represented by y. Script x and script y represent the set of possible values of x and y respectively. and there's m possible values of x and k possible values of y. And we've got training data from this joint distribution px, y, and we can factor that distribution as a probability on x and then a probability on y given x. And T is this true conditional probability matrix. So T is really our matrix representation of that true P of y given x, where the number in the ith row and the jth column represents the probability that y equals j given x equals I. So each row of this matrix is a probability distribution on y, and it represents what we believe about y given that x equals I. And this is what we're trying to estimate. We're trying to estimate T using our training data, using the modeling techniques, using all these tools at our disposal. And when we're done with our modeling, we're going to get a matrix Q, and Q is going to be our estimate of T. And so it's going to represent the probability under our model that y is j given x equals I. And so let's look at what these matrices might look like for these 5 different situations. So under perfect prediction, this would represent a place where the truth is a 0, 1 matrix. So for every x, you can know the y, the right y with certainty. And on the other extreme, the ignorant model would represent where we don't know anything about the problem, so all we can do is guess 0.5 for each value of y, regardless of the value of x. The naive model is a little better. At least we're able to look at the y values and see that, 20% of the time y is true. So we can guess that 80% no and 20% yes for each of the values of x. But we're not making any distinctions between the x's still. And you can imagine a situation where the truth looks something like this. Each x has a different row. Maybe the y's are in some certain range of value. In this case, the y's tend to be between 0.04 and 0.25. And your model is making estimates of each of those rows. And so what you're really trying to do is to see, are my q's, the values in my q matrix, close to the values of the T matrix? So we want to start thinking about how we would measure that and how we would answer some of these questions. So that's for the first question, where we're trying to get at, is my model close to the truth? We want to really measure the differences between Q and T. But now, imagine we're now trying to address the second question, which is really just, is my model useful? So we can come up with an abstraction where we say there's some utility threshold, there's some place on this spectrum of performance. And if we're to the left of that, this model is useful. But if we're to the right of it, our model is not useful. So here's a situation which I call the happy place, which is you've got a utility threshold. Typically, the utility threshold is going to be to the left of the naive model. Otherwise, you wouldn't really bother to build a model to begin with. So you need to get past this utility threshold. And in this picture, we're already past the utility threshold. Our model is already good enough to be useful. And we still got some distance between our current model and the truth. So we could still try to push our model more to the left to get an even better model. Now here's another scenario we might be in where our model is not yet useful, but we still got some room to improve. There's still space for our model to improve because we can hopefully get our model closer and closer to the truth. But fortunately, the utility threshold is to the right of the truth, so it's possible to get something useful. Here's kind of the hopeless situation that I think many data scientists at one point or another have found themselves in, which is where even if you got to the truth, it would still not be useful. Even if you built the model that totally represented what's really going on, it just wouldn't be useful enough. There's just not enough signal in X about Y for you to do the kind of prediction you're trying to do in this particular use case. And the challenge with these situations is that we don't really know where the truth is. So we might know that we haven't reached our utility threshold yet, but we don't know if the truth is over here and we're hopeless, or if the truth is way over here and we should keep trying. So this is sort of the practical data scientist's dilemma, is that we don't know where the truth is. Now, another aspect of this model performance continuum is that we can actually quantify the numbers on this axis using information theoretic concepts such as entropy. And entropy is connected to log loss and maximum likelihood, and in future videos we're going to try to make this all really nice and precise so that it can be really well understood. But to give kind of a preview of what's coming, entropy represents your level of uncertainty. And that's why we're going to say to the left means lower entropy, means better predictive performance. And for perfect prediction, there's zero entropy. There's no uncertainty about y once you know x, and that's the best possible situation. But typically, we're going to be in a situation where the truth is such that the entropy of y given x is more than zero. Typically, we're not going to be in that situation. The best we can do is that we're still going to have some residual uncertainty in y after we know the value of x. Now, this naive model that we described, that's going to have a performance of h of y unconditionally. The entropy of y represents our naive prediction where we know the distribution of y, but we don't know anything about how y relates to x. And similarly, our ignorant model is going to be an extreme situation where y is the uniform distribution. And this is going to be a very nice mathematical model because the difference between the naive model and the truth is going to be represented by a mathematical quantity, which is called the information that x has about y. And so this makes a lot of sense. We've got some uncertainty about y. We've got some uncertainty about y after we know x. And the difference between those two is the information that x has about y. So the more information x has about y, the closer the truth is going to be to zero. And our current model, that performance is going to be represented by something called the cross entropy, which can be decomposed into a sum of two pieces. One is the entropy of the truth, h of y given x, and then the second term is something called the relative entropy, also called the Kullback-Leibler divergence, which is a measure of distance between the truth and our model. So we can think about the performance of our model as being some irreducible entropy that's given by the truth, and then a penalty part that we can reduce if we brought our model closer to the truth. So hopefully this is illuminating, and we're going to dive more into the details of how to define these numbers and what they mean and what it means for the practical data science in future videos. So thanks very much for listening. Please like and subscribe. Keep watching. I'll be putting out more content on this subject. Leave a comment below if you'd like to start a conversation. And please sign up for an account at www.numeristical.com. You'll be added to the mailing list, and you'll be on the Slack channel for some of our future live events. Thanks very much, and have a great day.